Okay, so welcome back to part two of evaluating limits analytically. And so what we're going to do is we're just going to grind through these and see what happens. All right, so up here, left-hand corner, starting with this one, the limit of 2x plus 1 as x approaches 3. Okay, looks like a polynomial to me. Direct substitution. 2 times 3 plus 1, 6 plus 1, 7. So then we say that the limit of 2x plus 1 as x approaches 3 is 7. And I'm done. That was easy. No reason to think it wouldn't work, but I'm glad it did. All right, the limit of negative x to the fifth as x approaches negative 2. Again, looks like a polynomial, so I'm just going to use direct substitution. So I have negative quantity negative 2 raised to the fifth. Let's see, negative 2 to the fifth is negative 32, so negative 32. And that gives me 32. So then I say that the limit as x approaches negative 2 of negative x to the fifth is positive 32. This seems easy. Am I really just plugging these things in and grinding them out? I hope it doesn't get any harder. All right, so limit of 2x squared minus x plus 7, that's a polynomial, so I'll try it again. I got 18 plus 4. 18 plus 4 is 22, so then the limit as x approaches 3 of 2x squared minus x plus 7 equals 22. Okay. More? Okay. Limit of 3x cubed minus x to the fifth. Okay, that is polynomial, so I'm just going to plug it in again. I have 3 times negative 2 cubed minus negative 2 to the fifth. Negative 2 cubed is negative 8. 3 times negative 8 minus negative 2 to the fifth is negative 32. 3 times negative 8 is negative 24 plus 32. And that's going to be, what, 8? So then the limit as x approaches negative 2 of 3x cubed minus x to the fifth is, it's ugly 5, but okay, 8. All right, here's the first one that's got me a little bit worried because now I have a fraction. I'm worried about the denominator being 0. So I'm just going to do direct substitution and hope it works. We're taking the limit as x approaches 1, so this would be 3 times 1 minus 7 divided by 1 plus 1. 3 times 1 minus 7 is going to be a negative 4 over 2. That's a negative 2. So then we say that the limit as x approaches 1 of 3x minus 7 over x plus 1 is negative 2. This seems pretty straightforward. Okay. More and more and more of these. All right, so we're taking the limit. Again, rational function, but I'm going to plug it in and see what happens. So I have 5 times negative 1 plus 3 divided by negative 1 squared minus a negative 1. 5 times negative 1 is negative 5 plus 3 over 1 plus 1. I think I've got a negative 2. So then I have that the limit as x approaches negative 1 of 5x plus 3 over x squared minus x is negative 2. These are making me happy. Oh, a root. All right, what's the rule for roots? Well, the rule for roots says direct substitution. Right? So I'm going to use direct substitution. That's going to give me then the square root of 4 to the fourth plus 2 times 4 squared plus 1. 4 to the fourth, I have no idea. 4 times 4 is 16. 16 squared, 256, 512? 512, I think. Nope, 256. The root of 256. 4 squared 16 times 2 is 32. Plus 1. Square root 256 plus 32 plus 1 is going to give us 289. Is that a perfect square? I think so. The square root of 289 is 17. It's almost like someone made that to work out. So then we say that the limit as x approaches 4 of the square root of x to the fourth plus 2x squared plus 1 is 17. Okay. You'll notice that I'm getting into the habit of writing out the entire thing at the end. I know it seemed cumbersome, but I want to be correct. Right? Ugh. Okay, direct substitution is what I always try. 2 times 1 plus 1 cubed divided by 3 times 1 squared plus 1 to the 3 halves. 2 times 1 is 2 plus 1 over 3 plus 1 to the 3 halves. Let's see, 2 times plus 1 is 3. So I've got 3 fourths to the 3 halves. Now here's my question. Am I done? Can I leave it like that? I mean, sometimes I would say yes, sometimes I would say no, because we could simplify this, and we could call this the square root of 27 over 8. Now, how did I get the square root of 27 over 8 out of this thing? All right, so how did I get that again? What does a fractional exponent mean? The denominator is a root. The numerator is the exponent, so 4 raised to the 3 halves means square root of 4 cubed. Square root of 4, 2 cubed, 8. The numerator, it's the square root of 3 cubed. Root 27. I think we could go one step further and call that 3 root 3. And so we could get that this limit is 3 square root 3 over 8. All right, this one looks ugly. It's just big and nasty, but once again, it's a root with a integer index, so we're good there. So I think I'm just going to try direct substitution. So that's going to give me the square root of negative 5 to the 4th plus 2 times negative 5 cubed plus negative 5 squared cube rooted. So then it's going to be the cube root of the quantity, negative 5 to the 4th. I need a calculator for that. 625 plus 2 times negative 5 cubed, so plus a negative 250, plus I can do that one in my head, 25 squared. So I got 625 minus 250 plus 25. Cube root of 400 squared. Let's see. 400 squared is 160,000. So the square root of 160,000. I'm sorry, not the square root. I meant the cube root. And so let's see what that gives me. What's the cube root? 160,000. Ooh, it's not going to be pretty, but I think we can simplify it. Let's see. 160,000. Let's see. I can take out 1,000 and make that 1,000 times 160 because 1,000 cube roots nicely. Now I'll look at 160. 160 is 8 times 20 and 8 cube roots nicely, and there's nothing pretty in 20 for cube roots. 4 and a 5, yeah. So I got a 10 and a 2, so that's going to give me then, just move this out of the way, 10 times 2 is 20 times the cube root of 20. And so there's our limit. Now this is one where I am not actually going to rewrite this because I just literally don't have enough space. Right? So I'm taking limits. I'm taking limits analytically. I'm just literally plugging in, grinding it out, plugging in, grinding it out, because every single time direct substitution worked. I didn't run into any issues with direct substitution. Right? All right. How about if someone asks us to evaluate a limit only if we had a graph of the function f and g? Okay. So here I have a graph. The pink one is f, and the blue one is g. Now, as we've talked about before, I wish I had a tool that could draw these nicely. Okay. All right, so let's see what's being asked here. What is going on here? I think that's missing its arrowhead. My job is to take the limit of f of x plus 5 times g of x as x approaches negative 2. I have no idea how to do that, but I know how to use limit laws. So I'm going to think of this as the limit of f of x as x approaches negative 2 plus 5 times the limit of g of x as x approaches negative 2. And I'm going to evaluate those two pieces. So again, f is the pink one, right? Now, it's a little bit hard to see on here, so I'm going to highlight it with the yellow. This is the x-axis right here, and this is the y-axis right here. So if I am taking the limit at negative 2, I need to talk about what the graph is doing here, from the left side and from the right side right there. And so where is that graph going? It looks like it's approaching 1. So then the limit of f of x as x approaches negative 2 is going to be 1 plus 5 times, now we're going to do the same thing with g. Well, g is here, so from that left-hand side, from that right-hand side at negative 2, it looks like the y value is negative 1 there. So that'll be 5 times a negative 1, and so it looks like we have a negative 4. So then the limit as x approaches negative 2 of f plus 5 times g is negative 4. Okay. All right, same question. Find the limit using the graph, but now we're taking the limit at 1 of f times g. Right? Well, at 1 is going to be here because that's 1. And so what is the limit of f there? Well, the limit of f from the left-hand side is going to be, looks like 2. Right-hand side, 2. So that's going to be 2 times, we have a jump right there, a break in the graph. What does that mean about the limit of g? Well, that means the limit of g does not exist. And what's 2 times does not exist? We say that the limit of f of x times g of x as x approaches 1 does not exist. All right, third one, same question. Again, we're taking the limit as x approaches 2 this time of f divided by g. So it is a different place on the graph at positive 2, and we're doing f divided by g. All right, so let's see. I'm going to get rid of everything I don't need on my picture over here so I can focus on what I'm talking about here. Again, this is the x-axis. This is the y-axis. Right here is 2 on the x-axis. So the limit of f looks like it's about 1.5 from the left, from the right. And it looks like g is 0. So I think this is going to be 2 divided by, what's divided by 0 mean? Well, 2 divided by 0 means I'm going to have some sort of a vertical asymptote. So is the answer this? Or is the answer this? Or is the answer this? Is the answer infinity, negative infinity, or does not exist? This is a tricky one. So what I have to do is I have to look at the graph a little harder. Right? So I'm going to come back over here and I'm going to stare at this thing a little bit longer. Give it a second to come back into focus. It doesn't like to zoom in and then move around. Okay, so let's talk about what we can all agree on. We can all agree that at 2, f is a positive number. Regardless of whether you're coming in from that left-hand side or that right-hand side, you're a positive number. But g down here at 2 from that left-hand side is negative, and from the right-hand side is positive. So dividing by 0 or dividing by very, very small numbers close to 0 gives you very, very large answers, which is why we get those vertical asymptotes. I'm hoping that you discussed that in college algebra. But over here, since on the left we're dividing by a negative number, that really means we're going to get a vertical asymptote going down. And on the right, because we're dividing by a positive number, we're going to get a vertical asymptote going up. And then what was the rule for vertical asymptotes when one side went up and one side went down? Well, that was the limit as x approaches 2 of f divided by g does not exist. To be positive, both sides would have to go up. To be negative infinity, both sides would have to go down. We don't have either of those occurring. So we have a true does not exist for our limit. Okay? All right. So moving on, let's start developing these strategies. Here's the most powerful one we're going to do. Okay? Every limit we've done so far, where we were asked to evaluate them analytically, was something where direct substitution just worked. Every single time we plugged in, it worked. It worked, it worked, it worked, it worked, it worked. It made it easy. But what do we do when we have limits where it doesn't work? What if someone gave us this limit? Now, if I try to do direct substitution here, what am I going to get? Well, I'm taking the limit as x approaches 1. 1 squared minus 1 divided by 1 minus 1, 0 divided by 0. As we discussed earlier, a long, long, long time ago when we were looking at these things graphically, like a week ago, we said that that usually meant that someone punched a hole in the graph. And if there's a hole in your graph, then we can find a limit because we can approach from the left and we can approach from the right and we can figure out where that hole is. I don't want to have to graph this thing though. So how do I find the value when direct substitution fails me? All right, so here's the rule. The rule says let c be a real number and let f of x equal g of x for all x not equal to c in the open interval containing c. If the limit of g of x as x approaches c exists, then the limit of f of x also exists, and the limit of f of x is equal to the limit of g of x. How do you feel about this? Okay, let's go over here, and let's go over here to Desmos and take a look at something. All right, we were just looking at the function f of x, and it was defined to be x squared minus 1 divided by x, was it minus 1 or plus 1? Minus 1, I think, right? Take a look at the graph. What does it look like? It looks like the line y equals x plus 1. In fact, if I graph those two, you can't tell them apart. If I turn this one off, the red one shows back up. I turn it back on, the red one you can't see. Okay? Why do those two graphs look exactly the same? Right? So let's go back over here. And let's go down to the blank page so we can talk about it. Okay. All right, so suppose that we have the function f of x is equal to x squared minus 1 over x minus 1. Now I'm hoping that when you look at that numerator, you see the difference of squares. So we could factor that numerator into x minus 1 times x plus 1 over x minus 1. And I want you to focus on this right here. Now, you might be tempted to say, cross those out, cancel them. But technically, we can't cancel them because they exist for a reason. They exist So that when we graph this thing, oops, geez, that didn't line up at all. So that when we graph this thing, we get that hole when x equals 1. Okay? Whoever made up this function wanted this function to have a hole in it there. And if I cancel those out, that hole disappears. But what I want you to think about is, think about what happens for any number other than 1. Like pick a number. Right? Let's say that x was 3. Well, then that pink thing is going to be 2 divided by 2, and that's going to just become a 1, and it doesn't do anything. If x was 5, that's going to be 4 over 4, doesn't do anything. It's just a coefficient of 1. In fact, for any value of x other than 1, that will essentially cancel itself. Right? You end up with a coefficient where the numerator and denominator are the same, and it just disappears. So what I'm getting at here is that the function f of x squared minus 1 over x minus 1, looks a lot like the function g of x, which is just plain old x plus 1. And these things look exactly alike everywhere except at x equals 1. But if we go back to that definition, where were we? We were here. If we go back to that definition, that's two functions that are equal to each other for all x's that aren't 1. And if this theorem of mathematics says that if you can find that g of x, and you can find the limit of that g of x, then that g of x is going to approximate the limit or give us a value for the limit of f of x. Right? So basically what we're getting at here is there are a couple of techniques for algebraically manipulating a limit. The direct substitution fails for us. Okay, now remember, this is only for the failure. This is only when direct sub fails, and it has to fail by giving you 0 divided by 0. Right? If you don't have the failure of 0 divided by 0, this doesn't work. So the first thing you always do is try direct substitution. Right? And so then the basic techniques we use to work are what we just did, that dividing out, where we factor the numerator or factor the denominator or factor both the numerator and denominator, find that common factor that's causing us problems, ignore it to turn f of x into g of x, use direct substitution on g of x, and find the limit. The other technique is going to be a rationalization technique that we'll use when we have roots like this one right here. Okay? But again, these techniques only work when direct substitution fails, and only when it fails in 0 divided by 0. All right, we'll come back and do those examples in the next video. We're already at 23 minutes. All right, so I'll see you back here for part 3.